Hello, my name is George Husack, and I'm a part of the class of 2024, and the title of my Comenius project is Propulsion Through the Ages, Advancing the Space Exploration and Scientific Research. Space travel is fascinating exploration beyond the Earth's atmosphere into the vast expanse of space. Over the years, rockets have taken many different trajectories with different goals in the space. The idea of space travel pushes the minds and imaginations of scientists to create innovative ideas for new technologies. These technologies help develop society and continue to evolve the world that we live in. The imagination of a person fosters questions like, how fast could we travel to Mars? How deep could we go into space? How often could someone travel to a planet in our solar system? All these questions can be answered by considering how efficiently a spacecraft produces thrust and propels itself forward. Throughout the years, scientists have explored the use of gravitational assist, chemical propulsion, and are looking to expand their knowledge into nuclear propulsion. Throughout this video, I will demonstrate how different propulsion systems work and how they have changed throughout history. In 1957, Russia launched the first ever satellite into space. 20 years later, the US began to launch its own satellites into space. In 1977, the United States launched two satellites, Voyager 2 and Voyager 1. These two satellites were vital in demonstrating the effectiveness of gravitational assist and how this extra boost can help keep an object in orbit longer, producing greater travel distances. Now you might be wondering, what is gravitational assist? Gravitational assist involves flying close to a planet to alter a spacecraft's orbit through its gravitational field, often increasing velocity and propulsion with less energy. Gravity is a force that attracts objects towards the center of a massive body. As a rocket approaches a planet, it experiences more attraction and alters the trajectory. The planet's momentum also affects the spacecraft's trajectory. The momentum of the system is conserved, with momentum gained by the spacecraft equaling momentum lost by the planet. The Voyager missions demonstrated this as the satellite's momentum increased while the planet's momentum decreased, even though it was very little. So below here is a picture of the trajectories that the Voyager missions took, and here's a picture of the Voyager 2 satellite. The Voyager 2 and Voyager 1 also used a lightweight generator to produce power for all the systems. This generator is called a radioscope thermoelectric generator, which produced heat through a plutonium decay, which then this heat was applied to thermocouplers and to generate electricity. So moving on to more of a modern day example of rocket propulsion, gravitational assist will always exist, and to this day we still use it, but more modern is chemical propulsion, which works by basically a rocket burns fuel in the engine to create hot gas, which is expelled out of the back of the rocket, propelling it upward. Fuel can be in liquid or solid form, but liquid creates more thrust and it regulates more, and it's easier to regulate. Thrust is generated by accelerating gas with faster gas creating a greater force. Fuel and oxidizer are injected into a combustion chamber before a controlled combustion reaction occurs. A nozzle attached to the chamber accelerates the high velocity gas, creating thrust and releasing exhaust gases that propel the rocket upwards. This can be seen through this image right here of just a general how chemical propulsion works. And then the most common use of it is in Falcon 9, which is SpaceX's main rocket, which uses liquid oxygen and kerosene as its propellants to put it into orbit. And then it uses a Merlin 9 engine, which can be seen here, where the kerosene and liquid oxygen get pumped into the combustion chamber and then expand into a hotter gas, and then goes out the bottom here as thrust, as exhaust and thrust. So the future of propulsion really that scientists are mainly looking at is nuclear propulsion, which utilizes nuclear energy, which is basically the energy released from the nucleus of an atom, either through the process of nuclear fusion or fission. This energy is incredibly powerful due to the fact that the strong nuclear force, which binds protons and neutrons together in the nucleus, is much stronger than the electromagnetic force that governs chemical reactions. Scientists have somewhat looked at this before. In 1961, in the NERVA, Nuclear Engine for Rocket Vehicle Application program, but it just wasn't, at the time, very practical and cost efficient. They're mainly looking at two different types of nuclear propulsion. So there's nuclear electric propulsion, which uses a nuclear reactor to produce heat, which converts the electricity for an ion propulsion system, which we already have developed. And this system basically accelerates positively charged xenon atoms through an accelerator grid using electropotential energy, resulting in high speeds of approximately 40 kilometers per second. Nuclear electric propulsion is considered more efficient because it has a higher specific impulse, meaning it can produce a greater change in velocity. And that can be seen in this image right here. And this would basically just allow the rocket to travel faster and longer distance, but using less propellant, because it's not gonna have to worry about always having to run out of fuel, because it's gonna use a nuclear reactor to produce that heat. And then the second kind of propulsion is nuclear thermal propulsion, which uses, again, a nuclear reactor to heat up hydrogen and convert it into a gas for thrust. And this process is going to use uranium atoms split through fission in the reactor core, releasing heat that is transformed to the hydrogen to expand and produce thrust through a nozzle. Again, this NTP, which is nuclear thermal propulsion, has a higher specific impulse than chemical rockets, due to the lighter gases being produced, similarly, this is based off of this form of propulsion will only be allowed to be used in space because it's just doesn't produce enough thrust to get the rocket off of the ground. And when people ask sometimes which one would be more suitable in the future, it's really hard to judge because they both are suitable in their own ways for different missions based off of the amount of thrust that the ion propulsion system uses. So that one would probably be better for longer distance, and this one would be shorter distance, but it's more reliable, I guess is a good way to say it. And then, so that's nuclear propulsion. So in conclusion, space propulsion is just an essential piece of technology in spacecraft that continues to help humans explore beyond the Earth's atmosphere. Without propulsion, rockets would never go anywhere. And I'll leave you with this thought. Whether rockets use chemical propulsion, nuclear propulsion, or gravitational assist to explore the universe, space exploration can continue forever. The only limitation is the human imagination to not be curious of new innovative ways to travel in space. Thank you for listening.